Okay, hello everyone. So this week we're going to talk about something that's a bit new that we don't normally talk about, which is AI and machine learning. Now, we're not going to really teach you how to do it. That's not the point of this week. It's a huge area. We couldn't possibly teach you in any video that we could possibly expect anybody to watch, not a single one. But there are quite a few things that sort of keep coming up between the technical press and even the actual news about AI, machine learning, and how things are going on at the minute. And it can be very useful to sort of see behind the scenes why these things work the way they do, and just have a sort of mental model of the sort of thing that's going on behind the scenes. And that's what we're going to cover today, something which is a very simple computational and mathematical model that is very loosely connected to what the things like GPT-3 and GPT-4 or Google's Bard are actually doing, but is still a model that you can actually understand and keep in your own mind of what's going on. So here is an article on somebody's LinkedIn page. This is a professor of human resources management, I think. An academic working in the field of human resources at Tilburg University. He had a reviewer reject his paper who suggested that he should read and familiarize himself with some papers, and the papers didn't exist. And from a tool which is admittedly very imperfect, he has reason to believe that what was generated may well be from something like ChatGPT. And this is something that's quite interesting. So the entire point of things like ChatGPT is to generate text. ChatGPT-4 can at least take input that isn't text, but it generates text. There are other systems that generate other things, but here we're talking about the text mode ones. And the things they generated, they certainly look like papers. So reference there, the impact of digital technology on leadership styles and performance, a systematic literature review, K. van der Meyden, DVF Beckers, and HJM ten Kluster, I think, in the Journal of Business Research 2019. That is a title. This isn't my field of research, never has been, but I could believe that title existed implicitly. Apparently, it simply does not. And that's sort of the thing. The machine learning model clearly knew what a reference was meant to look like, and it made things that looked like references. The fact that one of the most important things that a reference should have as a property is existence doesn't really feature in it, because that's not how they work. So, as I say, real machine learning models, very complicated, but just briefly to go through them, pretty much all of the current systems are what are called transformers. So that's a deep learning model, so lots of layers of machine learning-y stuff between inputs and outputs. But the important thing about it is this thing which is called the attention mechanism. So the idea of it is it uses context of how it's reached the current point. So, it's in the middle of telling you something, and it looks back, and it can look back theoretically sort of arbitrarily far to see how it got there, and based on how it got there, it works out where it's going next. That's a very, very, very simple overview of these kind of transformers, but that's the idea. It looks at where it's been, and it's been trained to go, given that that's the path I've had to get here, where do I go next? That's a training, creating those pathways. Given the states I've previously been in, what's a state I should be in next? And in particular, looking at GPT-4, they state that GPT-4 has a context window, which in this case you can broadly think of as sort of how many words back in the conversation it's been having with you it looks. That's very, very oversimplified, but broadly, of 8,192 and 32,768 tokens, and GPT-3 was using 4,096. GPT-3 was using 2,049 tokens, and GPT 3.5 4,096. So essentially that sort of shows what these models are doing. Then they're, in a lot of senses, they're really not intelligent. I wanted to say they don't work the same way a human does, but we actually don't really know how humans work. But the one thing we can say for fair degree of certainty is that what these things are doing is they're just saying, okay, given all the things that have been said in the last 2,000, 4,000, 32,000 words, given all of that context, what is the thing I should say next? And there is then a random element to it. That's why all these models have what's called a temperature, which is a measure of that randomness. And if you have the temperature turned up high, they're very random and they're highly likely to jump off onto a new path. If you have the temperature down low, they'll give very closed, very restrained answers that are highly likely to be the most likely outcomes of all the last whatever many thousand context elements they're working with. Now, these models are very large. They cost a fortune to train. They're not even cheap to run. There is some interesting stuff on rather smaller models. If you look at something called Alpaca Laura, which I actually just didn't bring up the page, but I may as well. This is just one. There are various others. These are rather smaller models, and they can produce really quite good results. So here, in their thing, they, train it, run it, and say, tell me about alpacas, and it'll tell you about alpacas. And this is a much smaller model that you can realistically run on an expensive graphics card. You couldn't run it on a cheap GPU, but you could run it on a workstation class GPU in a normal workstation. So you can actually get a lot further with simpler models than you would think, even though things like ChatGPT-4 do produce amazing results. But the question is, how far down can you sort of take this model? Can you take it down to the point where it's sort of something you can mentally keep in mind of what's going on? And I think, yes, you can, at the cost of obviously losing a tremendous amount of the power. It can no longer answer questions or do anything else, but you'll be able to see that a very simple model that I can actually code up here while you're watching is able to generate something that at least looks a bit like text. So, as I say, you have all this context, all this history. The ChatGPT models have thousands of elements of history. What about if we take it right down to the absolute minimum? And we have effectively no history at all. We know what state we are in, and we have rules for going from that state without knowing how we got to that state, just the state we are in. We have rules to going to the next state. And so here's that sort of shown diagrammatically. We are on a given word, word 1, and we know that if we are on word 1, there are 3 words we could go to, word 2a, word 2b, and word 2c, and we have a probability. The probability that given we're at word 1, we go to 2a, at 1 go to 2b, and at 1 go to 2c. And that's it. What we need to know is just those probabilities of the transition. And that is, of course, a finite state machine, which is an absolutely classic computational model. So even if you're not really interested in machine learning, which this isn't, this is way, way back from machine learning. I should say, as a sort of analogy, you could almost think of this being to something like ChatGPT as a transistor is to a CPU. There's some sort of linear connection between them, but there's massive scale differences. But this model, when you actually see it working, is something you can keep in mind and have some chance of understanding. So, in order to do this, you need a few things. First of all, you need some text. Okay, so here what I have is I have the complete works of Shakespeare. Now I got this from Project Gutenberg. One of the actual problems with the real AI systems at the moment are questions of copyright. This is one of the reasons why I have picked the complete works of Shakespeare, because it is undoubtedly completely out of copyright. So I've taken it from Project Gutenberg. I've stripped off all of the Project Gutenberg's header at the top and all the Project Gutenberg header at the bottom, which was not written by Shakespeare as far as I know. So we now have our stream of text. Now, if I go back to this diagram, what you can see you're going to wind up with in the end, effectively, is you're going to wind up with a list of words or some kind of data structure consisting of words mapping to other words with given probabilities. Now, there is no single data structure that matches onto that brilliantly, but to a degree, that can be mocked up most easily using associative arrays. So that's something like a map in C++ or a dict in Python. An earlier video we showed you how you'd write something called a hash table in Fortran, a language that doesn't have one built in. But I'm going to write this here in C++, and it's not going to involve any clever stuff. Most machine learning stuff is done with a GPU. There is no need to get that clever here. We are just going to do this on a CPU. And I'm going to do it in C++, because while this is much, much easier than anything in any of the proper machine learning models, it's still heavyweight enough that Python almost certainly wouldn't be fast enough for a video like this. And it won't actually be that much simpler either. Okay. So, I'm just going to move the microphone so that you can still hear me while I type. So I'm going to need a few headers, because you always do in C++, and I've already worked out what they're going to be. I'm going to need map, because as I say, that's a data structure I'm going to use. I'm going to use algorithm on the basis that I'm going to need to operate on some strings at some point. I'm going to include IO stream, because I'm almost certainly going to need to print something. I'm going to need fstream, because I'm going to have to read that file of Shakespeare in. I'm not going to embed it in my source code. And as I said, I'm going to need some strings. And I also said I'm going to need some random numbers, so I'm going to include random. So there we go. That is everything I'm going to need in this. And I'm not going to try and be clever. This is not going to be a particularly well-structured piece of software. And honestly, it's going to involve some slight misuse of C++ STL containers. But it's good enough for the purposes of showing what I want to show here. But I'm going to write it all as a monolithic program in main. Not a brilliant idea in general, but I'm going to do it. So first of all, I'm just going to create my IF stream, which opens my file, which is pg100.txt. So Project Gutenberg element 100 is a complete works of Shakespeare. Fine. Okay, I'm now going to need a string, which is going to be my current word. And I'll make some changes here. I'm just at the moment going to write something very, very simple, which just reads the things in word by word and prints them. So we're just going to print the first first 100 words, say. So do that. I'm then going to do while. There we go. I've actually created a variable now. So while I read from my file into my string, so that will keep going until I run out of words. And I'm just going to print them, each on its own line. And I'm then going to do increment I, if I is 100, break. Okay. Compile that. And important thing to note, equals and equals equals. In C++ and C, you really have to get those right, otherwise something like that will immediately terminate. So there we go. That is the first 100 words in this edition of the complete works of Shakespeare. And you can see we've kept all the things like commas and full stops in. That's potentially going to be a problem eventually, but we're not doing anything too clever here, so I'm not going to worry about that. What is more of a problem is all of these capitalizations. So really, if you're generating something properly, and certainly things like GPT-3, ChatGPT, Bard, all of them, they do generate things with proper capitalization. Here, what I'm going to do is I'm just going to quickly convert absolutely everything to lowercase, because, you know, words with different capitalizations are not actually different words. So, first thing here, I'm just going to transform my word to lowercase. Now that looks a bit weird, but it's essentially saying go from the start to the end of word, put the output in word starting from the beginning, and run the function to lower on each one. So if I now run that again, there we go, all of the capital letters are gone. So I'm not going to show it at this level of granularity all the way through, but that one, that's actually well worth knowing, because there is no really elegant way in C++ of transforming a string to all uppercase or all lowercase. This is the one I prefer. So at this point, I'm going to take out all of this stuff because we don't want to operate only on the first 100 words. We want to operate on all of them. So the key thing is, what I want to know is, given the previous word, what words come after it? So what I want to do is I first of all want to say, okay, I'm going to store another string, which is the previous word. And after I'm finished with whatever I'm going to do with the current word, I'm going to make the previous word be the current word. Easy enough. But what do I actually want to do in the meantime? So what I want to do is I want to say, I want to have a mapping from the previous word to the current word and how many times that mapping happens. So I want to keep track of how many times after this word I have this word. So this is going to look a bit weird, but I will show it and then sort of explain what I'm doing, which is I'm going to have a standard map, which itself takes a string for the key, but the value that it stores is another map, which also maps from a string, but this time maps to a double. Okay, and I'm just going to call that data. So the idea here is the outer map is saying, given the previous word, this string, I want to have a mapping between all words that follow the previous word and how many times they occur. So this is the previous word, the current word, and the number of occurrences. Now, one thing that is worth pointing out, because it's not something that's immediately obvious, but the way maps work in C++ is if I try and access an element of it that doesn't exist, that element is silently created, and it is silently created using a form of initialization that guarantees that this double element here is going to start at 0. So I can actually write my code in here to count the number of occurrences extremely simply. I can literally just say data of previous of word plus plus. So what I do is I look up in the outer map the previous word, that returns me this inner map. Within it I look up the word that I'm currently looking at, and then that returns me this double, and I increment the double. Okay, so on its own, that's that. So let's put in a bit of debugging stuff, because I'll run this, and I will say so that's how many unique words there'll be in. And let's see, say for example, the word king is followed by, and then I do data of king dot size. Okay. So what that is going to do is it's going to first of all calculate how every word, and so goes through the entire thing, finds every word, finds which word follows every word and how often it follows it. It's then going to tell me how many unique words there are in the complete works of Shakespeare, with certain things, things like full stops, commas, they will make words appear different. And it's then going to tell me how many words, unique words, come immediately after the word king. Okay, so I will compile that and I will run that, and this will take a second or so. There we go, 66,606 unique words, and the word king is followed by 263 unique words. So king is perhaps a bit too aggressive because Shakespeare talks about a lot of kings. So let's get rid of king and have, trying to think of words Shakespeare used. Let's say lest. I want a word that isn't too common. Okay, lest is followed by 53 unique words. Now, it's worth pointing out, you can already see that you are massively faster than things like ChatGPT. So that ran in a few seconds, and this one line, the bit that calculates the transition probabilities, i.e. if I am on a given word with what, well, it's not a probability yet, it's a count. How many words, how many of each unique word that follows a given word, what is the probability, so how many times does that following happen, basically. But that takes seconds. Training something like ChatGPT takes many hours on very powerful machines. This takes a few seconds on one processor. Okay, but now I'm going to do something else where I'm going to say the word lest is followed by okay, so this is one way of doing for loops in C++. It's one you might be familiar with. If you're not and you know Python, this is equivalent to doing for element in data structure. It essentially just automatically allows me to loop over all the elements in the data structure without having to worry about dealing with iterators explicitly. I'm going to use it here because it's really quite helpful. So I'm just going to loop over all the elements in data of lest. So this is looping over the inner of these two maps. So for the word lest, it will tell me, now it lets me access this map, the inner one. So one of the things about maps is when you access them like this, each element is not going to be the key, it's not going to be the value, it's going to be a standard pair. So I will print it by doing element.first, which is the first half of the pair, which is the key, which is this string. Then I'm going to print a space, and then I'm going to print element.second and a new line character. And what this should do is it should print every word that comes after the word lest in Shakespeare and how often it comes up. So there we go. After lest, you have lest at once, lest barbarism once, lest he 9 times, lest his 3 times, lest her once, lest Hector once, lest she 4 times, lest that 12, etc., etc. So this has told me something about the words, just the one word, lest, but it shows me what happens. So now the next thing I need to do is I need to go through all of these again. And as I said in this diagram, what you need is a probability. Given I am on a given word, let's say lest, I need to know the probability that I am on, that I transition to all of these other words. Okay. And obviously that's very simple. Knowing the count, you can calculate the probability very simply. Now, what I'm actually going to do is slightly different, because what I want to do is select one of these words randomly. And the easiest way of doing that is to not just have the probability of each of them, but have the cumulative probability. So I will say, you know, the probability that I have this one is whatever it is, and then then you have so you have P2A of that. Above that you have P2B, and you just, so long as all of these numbers add up to 1, these probabilities add up to 1, then you just select one random number between 0 and 1, and using the cumulative probability you can select one of each. That's mildly technical and it doesn't really change anything. Essentially, I'm just coming up with a way of selecting a word based on the probability of it occurring. So calculating the probability is very simple. What I need to do is I need to loop over, now not just the individual things for data of lest, I need to loop over all the words in data. So I'm going to have another one of those for loops, which is the outer element. That just loops over data. And then inside that, I have my inner loop, which loops over the outer dot second, which is this map. because this would be the first, outer dot first, this is outer dot second. Okay, so I'm looping over the inner, and what I want to have is I want to have a double, which is just a temporary value, and I'm going to store the count. No, yes, I'm doing this slightly wrong. So what I want to have is I want to have a number that adds up to the total number of words of any kind that come after my word under consideration. So I call that t count, and it's going to start from 0. So I set temp equal. So I'll do it first without that cumulative distribution thing. So what I would do first is I would just say, okay, so t count plus equals inner dot second, remembering again, of course, that second is this double, which is the count. Okay, and that's all that I need at the moment. When this loop finishes, t count will be the total number of words that ever come after the word that outer is currently working on. I then have another loop, which is exactly like that loop in structure, but this time what I would do is I would just do inner dot second divide equals t count. So that would now mean that this inner bit of the map carries the probability. Now, as I say, the easiest way of actually selecting a given item from a set of probabilities is not to calculate the probability of each item individually, but to calculate the cumulative probability of each item in the ordered thing. So I'm now going to switch over and do that. And the way I do that is I keep track of how many items there have been up to the current item. And I then modify the inner with that. So essentially it means at the end of this loop, what I have is not just for every given element I'm going through, I don't just have the total number of instances of this word, I have the total number of instances of this word and all words that I've already considered. So at the end of this, the value of this double here for the last one will be the same as the total number of words. I then divide it through by that total number, and each one will wind up with a number that goes smoothly from 0 through to 1, which is this cumulative probability density, cumulative probability distribution. So after I've done this, I really genuinely do have enough information to actually start generating some data. And another thing that's just worth doing here is to look at how much memory that I'm using. So the showing the memory didn't really work because it uses very little memory. I've tested it on another thing and tested it in a way that works better, and it uses about 50 megabytes of memory. So bear in mind, once again, things like GPT-3, GPT-4 use gigabytes, if not terabytes of storage for the system during training. We're using 50 meg. We are massively simpler. So the last thing to do is to actually start generating some phrases. Okay, so the first thing I need is I need a random number generator, which is always a bit overbuilt in C++. I can see why they do it, but it isn't easy. Okay, and then I want a uniform random number between 0 and 1 of type double. Okay, so I'll call that 0 to 1, Z20. So all that I need to do now is I need to create another string, which is going to be my prompt. I'm going to start with the string verily, which is something that one thinks Shakespeare used a fair bit. I believe he did. So there we go. That's a prompt. That is what you would type into something like ChatGPT. I'm not going to bother here with faffing around with taking keyboard input, although it's not actually that difficult. Maybe I will before the end of the video. So what I'm going to do is I'm going to get it to generate me 10 sentences. Okay. And each one is going to be 5 words long, including the prompt. Call that word. I did call that word. I'm going to call this I word just to avoid a reusing. Okay, so I word equals 0. I word less than 5. Okay. So what we need to do first of all is just print. Actually, I want it to start from the same prompt every time, so this should actually be in there. So for each word, we need to first of all print our current prompt, and we don't do anything other than print a space. After that, we don't want a new line because we want it to look like a sentence. I now pick a random number, okay, which is going to be between 0 and 1, and that does that. Now, what I need to do now is I now have my prompt, my word to look up, and I need to go over every possible word that can come over it and select one based on this random number. And that's not actually terribly hard. I say auto. I will just note one of the reasons that if you're not a big C++ programmer, this ampersand here, this means that I'm looping over using a reference to the underlying variables. I need that up here because I'm modifying them, but I need it in general because otherwise I'd be copying 50 megabyte chunks of data all over the place, which, well, not 50 megabytes, but decent chunks of data all over the place, which I don't want to do. Okay, so I look up my prompt in data. And what I just need to do now is just keep going. So I'm now going over all the elements which are possible things that can go after my prompt. And all that I want to do is I want to say if value.second, which is now that cumulative probability distribution, is greater than or equal to my selected random number, I set my prompt equal to value.first, which is the string I've just selected, and I break from this loop. Okay, and this shows very, very clearly that there is no memory. So I'm literally replacing this prompt word every time, and then it just goes back in and uses prompt again to look it up again and do the same transition probability. There is no memory, there is no history here, there is just a value, and all of the work is in doing that initial training step where I'm saying, given the state I am in, what is the probability that I will go to each of these other possible states? Okay, and then the last thing to do is inside this, I put in a new line so that all of my 10 possible sentences. Right. Honestly, yes, okay. It's amazing I got this far without having a compile error. So I missed a semicolon there, and I forgot what I'd chosen to call my random number generator device. And selected, it wasn't selected, it was select. Okay. This one is a more interesting bug. Ah, yes, of course. They say slightly overbuilt in C++ is a random number generator engine. There we go. So that's working. So if I now run this, I should produce 10 sentences of vaguely Shakespearean sounding, and I will give the game away here. Most of them, if not all of them, will be gibberish, but it will be Shakespearean sounding gibberish, I hope. No, I just produce a whole load of veriles. So I must have made a mistake in here. Let's try taking out the outer loop. I don't think that's going to be the problem, but it might make it a bit easier. Okay, so I just get a load of veriles. Second greater than equal to select. Ah, here we go. This is it. This line, people watching have probably been screaming at me. This shouldn't have just been equals because that's not changing anything. Inner.second plus equals temp. That's the thing that builds my cumulative distribution function. Okay. Verily he that depend on. So I'll put back in the code that generates the set of 10, and we shall see what we get. The thing, I don't do these videos live, but mostly the coding you see is done completely live. So mistakes happen. Okay, so here we go. So as examples, we have, verily did hate thee, Regan. It's a possible one. Verily bear him till tomorrow. It sounds possible. The rest of them are all pretty bad. It's more or less gibberish, but it sounds Shakespearean-y. And if I go back in and put in a different prompt rather than verily, let's go with king, which I know had a lot of nice possible things that could go after it. Generate it again. King of hard by that doesn't sound so good. King Edward, if I may, that's actually a sentence. King John, welcome is Licio or Licio, depending on how you pronounce that thing. I think it would be pronounced like a Latin type name, but I don't know. King Louis the Worst, forthwith. That's another pretty good one. So we've generated some things that sound pretty Shakespearean, and with nothing more complicated than a little bit of very simple probability. And so this sort of goes to show how it is that you can start using systems like this. As I say, this is massively, massively simpler than any kind of a machine learning model, but this is something which you can mentally get some sort of a handle on, which is that you just say, given the state I'm in, I know the probability I'm going to make a transition. And if I were to download a different set of text trained on, if I were to train it, say, on the works of Dickens, you would get a different answer. In fact, I will edit this video. I will go and get the works of Dickens, and we will see what we can see with Dickens. Okay, so we're back, and I've got not the complete works of Dickens, but some Dickens. So I don't know if he ever used the word king, but we shall try compiling with that word still as a prompt. So we have in there things that are not complete sentences, but, you know, King Edward's treasurer for the king pursued Perkin Warbeck the king who could gain the. They're parts of sentences. King is not a particularly good word here because it doesn't start a sentence, but Here we go, and it clearly sounds different. This version, trained on some work by Dickens rather than some works by Shakespeare, sounds much more 19th century rather than, I completely forget what year Shakespeare was active in, but it sounds extremely different. And ultimately, this is the thing. All of these text processing things, whether by simple means like this or very, very sophisticated means like the GPT programs, all essentially work by using context for what has gone before to say what is going to go in the future. And that's not to do down what people behind things like GPT-3 and GPT-4 or Bard or any of the others have done, which are remarkable. But there is no magic here. And this goes to show why you get results like that thing that I showed at the start. You get the production of things that look like references but aren't, because what it has learned is something that looks like a reference, whether it is a reference or not. And it hasn't got anything in its frame of reference, if you'll pardon the slight pun, for thinking that an academic reference should be correct. There is nothing built into its context system that makes it think that the fact that that paper doesn't exist is a problem. All that it knows is that what it has written has the form of being an academic reference, just as all this knows is that it has written something that has the form of Shakespearean text or Victorian text. Well, Dickensian in particular here. And that's basically the key thing here. As a mental model for thinking about these sort of things, they can do remarkable things. This model couldn't possibly pass a medical exam as GPT-4 can. But it is still just using context and information that it already has to work out what to say next. So when you see things like these GPT systems doing all these amazing things, bear in mind they are not intelligent, they are not thinking in the way that we would think about it. What they are doing is they are using an awful lot of information about how they got from where they started to where they are now, and they have a very much more sophisticated way of mapping that information into what they should say next.